Hi everyone, I'm Amir Jafari, your host, and we were discussing in the previous lecture Newtonian mechanics of simple harmonic oscillator, and in this lecture, let's continue uh, with Lagrangian and Hamiltonian formalism because again, we're going to need these concepts in other areas when we study quantum field theory, string theory, and condensed matter, etc. So let's have some equations and let's consider the problem of simple harmonic oscillator formulated in Hamiltonian mechanics first, and then move to Lagrangian mechanics, Lagrangian formalism, and then we can study quantum simple harmonic oscillator. Okay, so simple harmonic oscillator, we discussed this in the context of Newtonian mechanics last time. This is M, some mass connected to some spring. Well, you have Newton's law, MA, which is basically MD dt square. And Hooke's law gives you uh, this force. This is the restoring force. In order to have a simple harmonic oscillator kind of motion or approximation, you need a restoring force, a force which is against the motion. So the mass tries to move in this direction, but the spring tries to, pull it in another direction. So always the spring exerts some force in the opposite direction, opposite to the direction of motion of the mass. So this is the meaning of restoring force. When you have this restoring force as a linear force, kx, you can have higher order terms here, like this, in general. You can think of, as we said before, as a function of x, displacement, but you can Taylor expand it, and using the Hooke's law means that you are keeping only the linear term with a positive constant and negative sign in front of, okay? All right. So this was the Newtonian method. I will try to solve this differential equation, which is very common in this form, the Newtonian notation. X double dot means second derivative with respect to time. Omega is square x, and omega is the angular frequency. Okay. We talked about this in some detail. Now, we move to the Hamiltonian formalism. We're not going to talk about details of Hamiltonian formalism. Hamilton formulated Newtonian mechanics in, I guess, 1833. So it's an old, theory, and it's equivalent to Newtonian mechanics. It doesn't give you new, interpretation or anything like that. It's also equivalent to Lagrangian formalism of classical mechanics. But in some problems, this formalism is very, more useful or simpler than other formalisms. For example, Newtonian, uh, picture or Lagrangian picture. So we have to understand what's going on here as well. The Hamiltonian formalism is based on the energy, the concept of energy. Newton didn't use energy, didn't know anything about energy. Well, he probably knew because Leibniz defined some expressions and used them uh, for the energy of a particle. But he didn't use, it wasn't common in his day to use energy in the same way that we do today, and we separate it to kinetic energy, potential energy. Heat is a form of energy. We know this from the experiments of Joule, from thermodynamics, so on and so forth. So Newton was focused on the concept of force. Hamilton, on the other hand, was focused on the concept of energy. So he said that, look, this mass over here has in the simple harmonic oscillator, okay? So it means that we are keeping just this term, Hooke's law, Newton plus Hooke, okay? This mass here has some kind of a kinetic energy. What is it? It is, p squared over p is the momentum, by the way, mv, m mass, v, the velocity, and it has also kinetic energy, which is, potential energy, which is Uh, and also it can be written in terms of the angular frequency in this form. So it's the energy of the system. Well, you should know the simple harmonic oscillator upside down as a student of physics. For example, here, because we are talking about simple harmonic oscillator, we are not talking about these terms. So you should be able, in a blink of an eye, to get this potential energy. Remember, potential energy U is minus F force times displacement. In general, this is the definition here. And because F is the external force on the mass, minus kx dx. So from here you get, and because k from here is omega square m, so you get m omega square x squared, which is this. So this is the kinetic energy plus potential energy, right? This is the potential energy, this is the kinetic energy, this is the total energy of the particle, the mass connected to this spring. Okay, so long story short, energy is given by this expression. Let's rewrite it here. And then you say, well, I define this Hamiltonian, which is basically the energy of the system, as the total energy of the system. In general, this is basically many problems, a complicated, expression. Remember, in Hamiltonian formalism, if you're familiar, you already know in this formalism, x and p are kind of generalized coordinates. So x is not always simple position, simple variable as in Newtonian mechanics. X can be some angle, for example. So these are generalized coordinates. So it's common to, if you write it x and p, for this reason, it's common to write Hamiltonian as P and Q. I'm not going to go into details what I mean by this. I'm assuming that you're familiar with, you have some understanding from for this form of Hamiltonian mechanics. But the reason that we use this notation P and Q is because Q can be a generalized a coordinate, for example, some angle, some very complicated, intuitively quantity. So it's not always simple position like x. So, okay, this is your Hamiltonian. In this case, for simple harmonic oscillator, it is simple. And we have Hamilton's equations, equations of motion. I'm not going to drive them. I'm assuming that you are familiar with them. If you are not, just, trust me. dh over dx, if I'm using x here, x and p. So let's call them here x, p. So I'm using this notation here because the generalized coordinates here in this case, simple harmonic oscillator, are just x, position, and p momentum. We're not talking about sophisticated generalized coordinates. So dh over dx would be minus p dot, which means the time derivative of p. In general, Hamilton's equations would look like these. And for a system with n particles, so k, 2, 3, n, they look like these equations plus q dot. This is q is the generalized coordinate of the kth particle. pk is the generalized momentum or canonical momentum of the kth particle, so on and so forth. But here again, we have a simple system, so it's going to be x dot. Now, if you look at this, well, what is dh over dx from this formula? dh over dx is m omega squared, the only term where we have explicit dependence on x is the second one, the potential energy. So we're going to get m squared x from there, and dh over dp is going to come from the kinetic part, which is basically p over 2m. Now, in terms of velocity, in order to see this equation in a more familiar form, this is basically, sorry, there is no, messed it up here. Okay, dh over dp should be dh over dp should be p over m, which is basically the velocity of the particle. Momentum is mv divided by m is velocity. Now, Hamilton's equations say that this should be negative dp over dt, because this is dp over dt, p dot, and this should be plus dx over dt, right? So from here you see that, well, we already know this. This is just definition of velocity. So this equation, the second equation, doesn't tell us anything important. But from here, well, dp over dt is the force, like f, ma, or f, whatever. But a negative sign, it gives you m omega squared k, which is basically minus kx. So this is Newton's second law plus the Hooke's law. So you get the equation of motion exactly like what we got in Newtonian mechanics. Okay. So this is the Hamiltonian formalism. But the reason that we are going through this without delving into details of Hamiltonian mechanics is that this this expression is going to be used in our study of quantum field theory and maybe later string theory, etc. So this is very important to keep in mind. Okay, let's put it this way. Now we move to Lagrangian formalism. So this was the Hamiltonian formalism. Now in Lagrangian, so Hamiltonian formalism defines a function, which is basically total energy of the system, as a function of p momenta. So the sum of momentum, the plural of momentum, the momenta of particles, and also the coordinates, the generalized coordinates, positions, generalized positions of particles. So this function and with these equations are the central, concepts in Hamiltonian mechanics. In Lagrangian formulation, classical mechanics, you say that, well, instead, I am interested in a Lagrangian, a function, which is not a function of, remember, H Hamiltonian was a function of P and X. Well, forget about Q, generalized coordinates, etc. Momentum and position, okay? But keep in mind, positions might be, generalized coordinates in general. But here you say that instead of momentum, I work with velocity, which is basically, let's write this, by the way, as L, because clearly L is used usually for Lagrangian density in quantum field theory and field theory. So let's write it as L. So L is a function of x and velocity, which is x dot, okay, in general. So you say that instead of Hamiltonian, which is a function of momentum and positions, this is generalized, basically. Remember, position. Here I use position as independent variables and velocities, or x dot if it's time derivative. Okay. How these two are related? Again, we are not here talking about classical mechanics. You're assuming that you are familiar with this. You know that Lagrangian formalism is related to Hamiltonian formalism in classical mechanics, and they are Lagrange transforms of each other. So if you know H, you can get L and vice versa. Okay. So basically L or Hamiltonian, if you know Lagrangian, Hamiltonian would be P Q dot minus L. This is a Lagrange transform. Lagrange transform. And hopefully you know about Lagrange transform. Otherwise, let me know in comments and we can probably talk about Lagrange transform. Because from experience, I know that almost everyone, every student in physics knows about Lagrange transform, has heard about that. But many students have, almost no one has a very deep understanding of Lagrange transform. They use it as a formula without knowing the geometrical interpretation. You know, it's usage in thermodynamics, for example. You know, they don't have a big picture of what's going on. But you know, it's a simple transform, and I'm assuming here that you are familiar with this. If you have n particles, by the way, you're going to have some summation here, so it goes like this. Okay, so for this Hamiltonian, if you know energy of the system, the kinetic energy, P squared over m plus m x squared. The Lagrange transform, again, if you feel that you're not comfortable with Lagrange transform, let me know in the comments and we'll talk about this in another lecture. L turns out to be, well, H here, let me write this in an appropriate way. So, come on. No. This is H in terms of P and X to emphasize that H is a function of generalized coordinates, positions, and momenta, and L is a function of x and x dot, or velocity. It turns out that this is going to be v squared minus m omega squared. So there is a minus sign here, plus the fact that instead of momentum, you have velocity here. Okay. Now, in Lagrangian formalism, the central objects are one, Lagrangian, the definition of a Lagrangian as a function of x and x dot, positions and velocities, and also the Euler-Lagrange equation, which is dl dx dot dl dx. Again, if you have n particles instead of just one particle, n simple harmonic oscillators, you're going to have k index here for each coordinate. Okay, this is called Euler Lagrange equation. So with this, so in any problem, any given problem, you need to know the form of Lagrangian. If you don't know it, you can look at the Hamiltonian if it is given, and from Hamiltonian, using a Lagrange transform, you get the Lagrangian. If you don't know the Hamiltonian, you don't know the Lagrangian, but you know the equation of motion, you can write down, you can guess, it's basically by guessing, a Lagrangian which gives you the equation of motion when you write the Lagrange, the Euler-Lagrange equation, okay? So for this Lagrangian, the Euler Lagrange equation would be like this. Let's get dl over dx, and let's get dl over dx dot, and then we can write down the Euler-Lagrange equation like this, dl over dx. So let's get this first, dl over dx, obviously m omega x, right? And the partial derivative of L with respect to x dot, which is basically, this is the x dot, or v, it's going to be mx dot, right? So This gives you d over dt of dl over dx dot. Taking another time derivative is going to give you double. So from here, you have mx double dot equals minus m omega square x, which is basically kx, and this is basically f or ma, right? Again, Newton's second law plus Hooke's law. So you see that this is the Lagrangian for simple harmonic oscillator, and this is the Hamiltonian for simple harmonic oscillator over here. Okay, so in short, we have Hamiltonian p squared over 2m plus m omega square x square, and Lagrangian is the Lagrange transform of this, and it is given by 1 half mx minus x squared. So this is basically the kinetic energy minus potential energy, and this is kinetic energy and plus potential energy. Okay, and potential energy is 1 half kx squared or omega square x squared, which is basically, as I said previously, u is defined as negative integral of f dot x, and from here negative kx dx, and this gives you, because it's a conservative force, you can define the potential, otherwise you can't. Okay, so this is the Hamiltonian and Lagrangian formalism of simple harmonic oscillator. And if you now you know the position in 3 dimensions, or like let's restrict ourselves and to 1 dimension. So you know that the solution is something like this, as we said before. Okay, and in the next lecture we're going to see that how this moves actually. This gives us something similar in quantum mechanics, but if you can write this also as a cosine omega t, b sine omega t. A and b depend on your initial conditions. If you use these, you're going to see that the total energy of the system, which is the Hamiltonian, or this expression, would be something like this. Well, let's, I made a mistake here. Let's call this constant something else. Let's call this b. Okay, let's because this a is the amplitude. So I don't want to. Let's call these alpha and beta. Okay, these constants. Okay, and you know that from xt0 initial conditions like this given, you can get these constants. So this is the total energy of the simple harmonic oscillator, and A is the maximum displacement. It's basically 1 half kx max. Okay. In quantum mechanics, when we treat simple harmonic oscillator quantum mechanically, we're going to see that the energy of the system cannot be zero. Here, classically, if there is no motion in the simple harmonic oscillator, the mass is just at rest, the energy of the system is zero. Look at this equation here. This is the energy of the system, the Hamiltonian. If x is zero at the equilibrium point, mass is just resting there, and velocity is zero, so momentum is zero. So Hamiltonian, the energy of the system of the classical simple harmonic oscillator would vanish for a mass which is at rest, no motion, no oscillation, nothing. So the ground state classically has zero energy, but in quantum mechanics, it turns out that the minimum energy is something like this. Okay. So, and other energies, excited levels of simple harmonic oscillator go like this: h omega plus h omega e2. If you increase energy of the simple harmonic oscillator, the energy will basically increase discretely, not continuously, and it goes like this, plus. So in general, what you get is En, nth excited level of simple harmonic oscillator is n h omega plus h omega, which can be written as h omega n plus 1/2. So this equation is super important, and we're going to get this kind of, not directly, yeah, we're going to get this actually in the next lecture. And this plays an important role in field theories and, relativistic quantum mechanics and string theory, etc. This is the starting point of, understanding many phenomena in particle physics, statistical physics, in condensed matter physics, say. So you have to remember this basically. But I guess that's it for the classical mechanics of simple harmonic oscillator. We said almost what we need and other courses in terms of equations and results for classical simple harmonic oscillator. In the next lecture, which is going to be hopefully the last lecture in this series, we're going to talk about quantum simple harmonic oscillator, and then we're going to finish this course and we'll move to, we're going to use these results in other lectures. More importantly, in our discussion of quantum field